Today's paper is Neural Architecture Design for GPU-Efficient Networks. The authors of the paper state that most of the optimized deep learning models do not leverage the architecture of modern GPU for fast inference, and leads to suboptimal performance. To solve this problem, paper proposes a network called GNets, referred to as GPU-efficient networks. The model achieves 81.3% top 1 accuracy on ImageNet classification, and it's 6.4 times faster than EfficientNet on GPU. General ideas are the followings. Low-level convolutional layers prefer full convolutions, and high-level layer prefers depthwise and bottleneck structure. Based on the findings, the authors built a family of GNet using a lightweight NAS algorithm. The model uses local linear regression NAS to find a family of GNet models. Starting from the initial structure, the method learns a linear model to predict the accuracy of a given structure. The algorithm is a very simplified version, meaning the model does not use SE block, transformers, or dropouts. The authors focus on regularized structural space where the main body of the network consists of several superblocks without skip link. The network is called masternet. Each superblock is stacked by several basic blocks of the same type and width, and a superblock is parameterized by its depth, width, and stride. Authors also consider three basic blocks in figure B: convolution block, bottleneck block, and depthwise block. As shown in the figure, XX block is a stack of two convolutional layers. BL block is a full convolutional layer with bottleneck structure of ratio less than equal to 1. The depthwise block is a depthwise convolutional layer with inverted bottleneck structure of ratio greater than equal to 1. A basic block is always wrapped inside a residual structure. If the input and the output shape do not match, the identity link is replaced by a projection layer with downsampling that uses stride of 2, and this is shown in figure C. The authors first designed experiments to benchmark the inference speed of three basic blocks on GPU. Figure A shows varying latent speed on the batch size. The size is varied from 1 to 128, and inference latency is measured on ResNet 50, ResNet 152, MobileNet v2, and EfficientNet B0 networks. In the figure, the inference latency is not a constant value but a decaying function, because a large batch size allows GPU to do the computation in parallel. Due to this reason, the authors state that we must specify the batch size when comparing the inference latencies of different networks. The flop is also a popular index to measure the network efficiency on edge device. The same way as testing different batch sizes, the authors check whether the inference latency is still in proportion to the flops on GPU. Figure B shows the inference latency against flops for ResNet, MobileNet v2, and EfficientNet at batch size 64, and figure C shows scatter plot of the model sizes. As shown in the figure, it is clear that the inference latency on GPU depends on neither flops nor model size at all. Now, this figure shows profiling of the three basic blocks. The width of depthwise block is set to be the number of channels of the depthwise convolutional layer, and its bottleneck ratio is redefined to be 1 over R. Three profiling networks only use one of the three basic blocks with the same width. Stride is set to 1, kernel size to 3 for all the blocks. To benchmark XX block, the profiling network places 5 blocks into the network. For bottleneck block and depthwise block, 10 blocks are used to ensure the same visual region among the networks. In figure 3a, XX block is compared against depthwise block on their various bottleneck ratio and block widths. With smaller ratio, the inference latency of depthwise block is smaller than XX block. Now, XX block is also compared against bottleneck block under the same setting, and this is shown in figure 3b. When ratio is 1, bottleneck block is slower than XX block since 2 bottleneck blocks of ratio 1 is clearly larger than 1 XX block. Based on figure A and B, the authors claim that it's reasonable to only use bottleneck block or depthwise block in network design. The plot in figure 3C and D show network latency against the network size. The authors find that XX block is actually very efficient under the same model size. The profiling results show that if XX block are approximated with bottleneck or depthwise block, the approximation loss is in proportion to the intrinsic rank of the original XX block. If the XX block is nearly full rank, ratio should be set to 1 in bottleneck or depthwise block, and authors say that this is actually inefficient. So whether bottleneck or depthwise block is more efficient than XX block on GPU depends on whether a particular layer prefers low rank structure or not. The authors analyzed the intrinsic rank of convolutional kernels in different stages. They consider 3 networks consisting of only XX blocks. These are ResNet 18, ResNet 34, and lastly, Profiling Net, which was manually designed by the authors. All 3 networks are trained on ImageNet dataset, and the plot shows the singular value distribution of convolutional kernels in different stages. From figure A to C, it's clear that the singular values of high-level layers decay much faster than low-level ones. Based on the observation, the authors conclude that it's reasonable to use convolutional blocks, which is XX blocks, in low-level stages and bottleneck or depthwise block in high-level stages to maximize GPU efficiency. Based on the findings that low-level layers should use XX block and high-level layers should use bottleneck or depthwise blocks, the authors of the paper designed a network called MasterNet. First, the authors designed 20 networks to obtain good initial structure. All the networks were designed to have latency around 0.34 milliseconds per image at batch size 64. The detail of the best 5 networks are shown in the table. C denotes a single convolutional layer, and X denotes XX block, which is just a stack of 2 convolutional layers, and B denotes bottleneck block, and D denotes depthwise block. In the last column, it reports a top 1 accuracy on ImageNet dataset. And starting from the initial architecture, which is the MasterNet, local linear regression NAS is used to optimize the structure of the network. And using the algorithm, the network finds light, normal, and large family of networks with different number of parameters. For more details of neural architecture search method, I suggest reading the paper in detail. Finally, the plot shows performance of light, normal, and large GE nets on V100 and T4 GPU with FP16 and Int8 precision. As shown in the table, GNet normal is 6.8 times faster than the EfficientNet B2, and GNet large is 6.4 times faster than the EfficientNet B3 architecture. Link to the paper and some useful resources will be provided in the description. That's all for today, and I'll see you next time with a new paper.